I want to use this opportunity to compare some different technologies and see what lessons from the past we can apply to the future superconducting supercomputers that you folks are building. Some of this material will be based on my book, The Physics of Computing, which I wrote for a new course at Georgia Tech. In particular, I will talk about classic CMOS properties here, and then we will move forward. Well, we will move forward to look back at the VLSI era, see what approaches we use then to try to get a handle on the challenges in this new era of VLSI, and we'll see how that might provide some lessons for the superconducting supercomputer era. Okay, so let's remind ourselves how a static CMOS inverter works. Okay, so when the input is 0, we have a pull-up transistor, which is a p-type transistor, which is on, and that connects the output to the plus power supply. And then when we set the input to 1, that pull-up transistor comes off, and the pull-down transistor, which is an N-type, comes on, and we connect the output to the negative power supply or ground. Okay, so the first question that comes to mind is the static behavior of this circuit. We have some noise back there somewhere. Well, somebody could mute your microphone.
Yes, please do that. Let me see. Looks like the only mic is mine, and now it's stopped, I believe. And it wasn't me.
Okay. So we have a scale of voltages in which the inputs and outputs can reside. VDD at the top and VSS at the back. So in steady state, as you saw, these voltages are the logic levels go to one of the power supply levels, VDD or VSS. But setting a single voltage to be a logic level is unwise and really, really impractical. So let's come up with some ranges for voltages. So let's come up with a range of voltages that represent a logic 0. Okay, so anywhere from VSS or ground up to this V sub L level, that's a logic 0. We'll have a range for a logic 1 from VDD down to VH. You'll notice there's a gap there. Okay, so what do we do with that gap? Well, we could define VH and VL such that those levels touch, but then we have some possible confusion when a signal is right around that transition level. So it's really better to define a range of unknown values, which we often call X. Okay, so as a logic signal transitions, it will go, say, from 0 through the X range up to 1, or from 1 through the X range down to 0. We don't want it to end up in the X range, because then we don't know what gate the value is computing, but wants us to think it's computing. But we do want to have a separation zone between a logic 1 and a logic 0. We don't want just a tiny amount of noise to send us directly from a 0 to 1. Okay. We can start to think about how those logic levels play out with time. Okay, so we have a time axis here. We can look at this as in the discrete space where we start at a 1, we go through X, and we go through 0. We can then look at the continuous signals that are actually what the logic signals constitute on chip. And so in this case, we'll go down from the high power supply down to VSS, and we will cross the boundaries between these zones at different times. Okay, so first you see at time t1, we cross the boundary from logic 1 to logic x. And then at time t sub 0, we cross the boundary from the x region down into the logic 0. Okay? So, you know, while we can, we're basically taking this continuous signal and abstracting those into discrete values, 0, 1, and x, but we can assign real valued times for when these events occur, when it goes from 1 to x and when it goes from x to 0. Okay? So far we've been talking about one gate. What if you've got two gates, one that talks to another? Well, we have V output low, which is the output logic, output voltage for a logic 0 from the left-hand gate. Okay? And we have V output high, which is the output voltage level for a logic 1 for the left-hand gate, right? And so we want the right-hand gate to see a logic 0 when the predecessor is sending a logic 0, and a logic 1 when it sees the predecessor is sending a logic 1. Okay, so the input gate has its own levels. It has a voltage level, the input low, that is the maximum value at which the gate will consider that input to be a 0. Okay. Then we have a V input high, which is the minimum voltage at which it's going to say, oh, this is a 1. Okay, so clearly we want V output low to be below V input low. Okay, otherwise, the left-hand gate could think that it's sending a logic 0, but the right-hand gate thinks it's an X. And similarly, we want V output high to be larger than V input high, because if the left-hand gate's sending a 1, we don't want the right-hand gate to think it's an X. Okay? And so the difference between the output and input levels is what we call noise margin. Okay, and we have noise margins on the low side and on the high side. In some of the older logic technologies, the high and low noise margins can be very different. They're more symmetric in CMOS. Okay. So moving on to more dynamic behavior, here is a simple model of an inverter. Okay, so the two axes are the input voltage on the x-axis and the output voltage on the y-axis. Okay. So let's draw a curve that shows the relationship between, where is this thing? There we go. That shows a relationship between the input voltage and the output voltage. Okay, so we look on the left-hand side, you see that at very high voltages, then excuse me, at very low voltages, the output is high, and at high input voltages, the output is 0. Okay, so basically we have taken this the axes here, and we've changed the origin to be in the middle of these logic ranges. Okay, that will help us see a little better what's going on. Okay. So at either end, the inverter saturates. That is, we change the input, we change it to be higher, or we change it to be lower, and that doesn't change the output. Okay, in between, this very simple model says there's a linear relationship. We know that gates are not quite that easy to deal with, but this model helps us understand the basic principles. Okay, so the slope there is the gain, okay? Logic gates are amplifiers, and so the gain is the difference, is the ratio between the output voltage and the input voltage, okay? So if we were building an audio amplifier, we would want gain to the 10 to 100 range, for example, right? Clearly, if we're designing a logic gate, we would like that gain to be at least bigger than 1. If it's less than 1, that means we put in a voltage that we think is solid on the input side, and it's going to give us potentially a not so solid logic level on the output side. Okay. Now let's look at a lower slope, right? You'll see this is a lower slope, and that means that we're moving the relationship between input and output into a less favorable location, right? And now, oh, excuse me. And right, so we want this slope to be, we can't make it completely vertical, but we want it to be standing up quite a bit. Okay. Now we can use this notion of gain to think about signals over time, okay, rather than a transfer curve. Okay, so here the x-axis is time. We have, once again, centered the voltage axis in the middle of the logic levels, okay? So the red line here is the output. For a gain of 1, we might have something like this, so that the output is the inverted, the mirror image of the input. If we move to a gain that is less than 1, the output transitions faster than the input does. And if we have a gain of less than 1, then the output transitions more slowly. Okay, so I haven't talked too much about the transistor curves yet, but let's take a quick look at that view. So this is the x-axis is the voltage across the transistor, across the channel, and the y-axis is the current through the channel. Okay, the red line here is the so here is the current curve for the for say the power supply voltage inputs. Okay, if we have a fast rising input, we will jump very quickly to one of these curves and then write it down to 0 current. Okay, as we're going as we're say taking the transistor down to or taking the gate down to 0. What happens if the input is slow rising? Well, the trajectory won't be as vertical, and so it will take longer to get to the maximum current that it can drive, and that means that for a big part of the transition time, it's not going to be drawing as much current as it could be. Compare the blue line to the red line. Okay, there's a big difference in area between the red line here and the blue line here. That area is lost opportunity to get the gate to get the gate's output to where we want to go. Okay. So one way to look at this is to compare a step input, which is a perfect transition, to a ramp input. And you can see that the step input here goes down and this is a circuit simulation, goes down reasonably fast. The ramp input goes down much more slowly. Okay, so we see that it takes more time to even get started. And then for any given voltage that we want to pick, the ramp, the response to the ramp input is considerably later than the response to the step input. Okay, so the gain of CMOS gates is not as high as the gain in some earlier technologies, bipolar technologies, for example. But at least we have some gain. Okay. So let's think next about signal integrity and noise. Okay. So here are two gates. Where can we have noise, unwanted values coming in? Well, we could have problems coming from either the power or the ground signals. Power and ground are not perfect signals. There will be some disturbance on them. Those can be transmitted to the outputs. There can be coupling within a gate from the input to the output. And there can be coupling between the input to one gate or the output of another gate to other wires that are completely different signals. Okay. So let's think for just a minute about transmission lines. For longer wires, we need to consider that the time it takes for a signal to go from one end of the wire to the other. Okay. So the wire is not an ideal conductor, and the time it takes to send from the left-hand side to the right-hand side is noticeable. And for very long wires, it can be a big part of the total delay. Okay. So the transmission line can have resistive components, capacitive components, and inductive components. For the moment, let's just stick with resistive and capacitive lines, or RC transmission lines. Okay, so we have on the left-hand side input, let's say it's a step function. We think of the transmission line as these segments. That's how we analyze it, as a series of segments, in this case, RC segments. So we can measure the voltage at different points along this transmission line to better understand the delay and the quality of signal that we will eventually get at the far end. Okay, so let's take a fairly simple qualitative view of what's going to happen here. We start with a pulse put at the input here. So in this case, the x-axis is not time, it is distance. It is distance from the source, from the input. Okay, so we put a step function at one end of the wire. What's going to happen? It's going to start traveling, but you'll see as it travels, the pulse will become distorted. It will start to lose its shape, right? And say here that the step becomes a pulse as we go down on the other side, and you can see that these things, both edges, suffer the same way. Okay, why does that happen? Well, let's go back for a moment to the transmission line model. That happens because there is resistance and capacitance along the entire length of the wire. It's not just what an ideal connector that's connected to some capacitance at the end. Each section of the transmission line contributes delay. We know that in an RC section that it takes some time to charge up that capacitor. Okay, and we should also expect some voltage drop across the resistor. Okay, but that first section, its output becomes the input to the next section, which further degrades and distorts that pulse. And then the output of that section becomes the input to the next section, which once again distorts the pulse. Okay, so that's why we see this kind of traveling along the lines. And this is a more quantitative look using circuit simulation. So we can see that if we start off with a nice clean pulse, that the orange line is the first, first part of the wire. It takes some time to get to the to where it's going, and it doesn't reach the final voltage that the input did. The gray is farther along on the wire. You can see that's more distorted, and the yellow is even farther along. So it is substantially delayed. Okay, if you look at the peak there, that's way behind where the pulse started, and it's significantly distorted. If I just showed you the yellow line, you probably wouldn't think pulse. Okay, so that's one view of delay in systems. Another important characteristic that we need to take into account is reliability, and that's a very complicated topic, but let's walk through some simple analysis. So this is a transistor here. We have the intrinsic properties of the materials in here give us certain energy levels at which electrons can exist, and then we can apply voltages both vertically and horizontally to control those. So if we want to move an electron from, say, the right-hand region through the middle P channel over to the left-hand region, you can think of having to get over energy barriers in order to move that electron from where it is to where you want it to be. Okay? So on the one hand, those barriers mean it's going to take time to get the electron moving, because it takes time to move those energy bands. On the other hand, those energy barriers are reliability tools, right? The bigger the barrier, the less likely it is that some electron's going to have the energy to jump over it. Okay? So we have a fundamental trade-off between how easy it is to change the value of a gate for performance reasons, and how easy it is for unwanted effects to inadvertently change the gate. Okay, and there's a couple of ways of looking at this. So a very simple analysis is to look at thermal noise. Okay, so we've got we're not operating these at absolute zero. They're operating at some approximate room temperature, right? So there'll be some distribution of energies for the electrons that appears as thermal noise. Okay, we can write a formula for the probability of error based upon the energy bands and the Boltzmann constant and so forth. So let's just for argument's sake say that we are willing to accept a 50% probability of error in a gate. Okay, that is, we're not going to take that as acceptable, but just to get an idea of the numbers involved, let's start with that. So then we can plug in a bunch of numbers. Assume 300 Kelvin temperature. We've got Boltzmann's constant. The probability of error translates in this formula to a coefficient of 0.7. That gives us a bit error rate of 2.8 times 10 to the minus 1, which is not bad, but it's could be better. Okay, so a more realistic model is to think about what it takes to charge the capacitance of the gate. Okay, so let's make a simple assumption about how much capacitance is at the input to a logic gate. We can then figure out how much energy it requires to charge that one bit, that one logic gate. And we can then plug that into a formula to tell us the probability of error, which is a very, very, very small number. So one of the good pieces of news about CMOS is that the probability of gates spontaneously changing their value is pretty low. Okay. But what about registers, flip-flops? Okay. So let's go back to having the x-axis be time. This is the output voltage of a register. Okay. In the case of metastability means that when we try to set the value of a register, it stays in this indeterminate state for some amount of time. Okay. So the traditional metaphor is you have a hill, you put a ping pong ball on top of the hill. You have two questions. Something's going to eventually blow that ping pong ball to one side of the hill or the other, right? But how long is it going to take to get there, right? So in this case, we start at some intermediate voltage inside the register. How long will it take for the register to settle down to its final value? Okay. The other question is, which side of the hill is it going to go to? And in fact, if we're sort of starting off in the middle, it could fall to the right or it could fall to the left. Okay. Which way is it going to go? And you know, it could go either way. One of those would be a lucky break, and the other would be an error. Okay. And we can analyze this behavior using a fairly simple model. So we have this. So we have some value we're setting up at the D input to the register. Okay. We expect that that input value will be presented to the input of the register for some amount of time before we actually set the clock level, right? So let's call that the setup and hold time, or TSH. Okay. Then we have some settling time, S here, for the amount of time it's going to take for the register to actually assume its final value. Okay. And then the total time, the T setup and H and the setup and hold and the settling time we'll call T. Okay, so we can apply some simple statistical arguments and come up with a formula for the probability of failure. Okay. You see that it's proportional to T. It's proportional to the ratio of the setup and hold time to the total time. And it depends upon an exponential that depends upon the settling time and the time constant of the register itself. So let's try to get a little bit of physical intuition for that. Let's say that we're setting this register at 1 gigahertz rate. Okay, we'll call the setup and hold time of 10 picoseconds. We'll call the settling time half a nanosecond. We'll call the time constant tau 10 picoseconds. Okay, so that gives the probability of failure once for one attempt to load the register to be 2 times 10 to the minus 24th, which sounds pretty low, right? But remember that this thing is running at a gigahertz. Okay, so the probability of failure over 1 second of operation is 2 times 10 to the minus 15th. And then you say, well, what's the failure over a day, a week, a year? You can see that these numbers keep getting bigger and bigger and bigger, right? So metastability was first recognized, I think it's safe to say, in the early 70s. It's a noticeable problem. Okay, you have to think about it. There are solutions. Luckily, one relatively simple solution is to put in 2 registers. So basically, you're giving the value an extra clock cycle to settle. This is remarkably simple. It drastically reduces the probability of a failure. So there are fancy things you can do, but there are luckily relatively simple countermeasures. This does cost you an extra clock cycle. That may not be a big deal in some things. It may be a bigger deal in others. Okay. So now that we've reviewed some basic properties of our the CMOS that we've come to know and love, let's compare MOS logic in general, and I'll tell you why in a minute, to Josephson logic. So we could consider adiabatic logic, but basically we use energy for each transition. Okay. We represent logic values using ranges of voltages. Okay. We have gain that helps us with noise immunity. We have dissipation, which adds some delay, but it also helps to dissipate certain types of noise. Okay. Josephson has quantized logic values at very small energy levels. It has no gain. You're pushing these things around, and you don't have dissipation. Okay. So there are some interesting challenges that you guys know much better than I do. Okay. So I think there is some philosophical inspiration that we can get from the VLSI era. Okay. And this was pre-CMOS. This was the NMOS technology, but I think that the basic attributes of MOS, gain and so forth, still apply. So let's remember what things were like in the 1970s and 1980s. In the early 1970s, it was very common for chips to be designed either by drawing on a piece of butcher paper that's rolled out on the floor, or perhaps directly cutting rubylith, which is an antique material that that most of you have probably never seen. Okay, my friend Lou Sheffer said that he designed a spectrum analyzer chip in the mid-1970s. He entirely wore out one electric eraser. He almost completely wore out another one. He finished the chip, it worked, and they said, I'm never going to do this again. And he went into CAD, and he spent many decades as a very well-known CAD researcher. Okay. When we get to the early 1980s, we see a place and route that's pretty successful. We also start to see the beginnings of logic synthesis. So we see much more automation. How did we get from this era of very manual design to plausible levels of automation? Well, it took some time, and it took algorithmic efforts, but it also took, so we say, methodology efforts to figure out what trade-offs designers were willing to make and embody some of those trade-offs in the CAD tools. And so I think a prime example of that is the generator. Okay, this is the cover of Carabine and Lynn Conway's book, and it shows you a data path that was created by a generator. That is a program where you could give it some parameters of what you wanted, and it would create the layout that embodies that. Okay, so this was not a one-off design. They could generate different types of layouts by giving different parameters to their generator program, and you could parameterize all sorts of things. The number of bits you could parameterize, in this case, I think the different functions that the LU did, and so forth. And it used a collection of algorithms that were tailored for different parts of the of that data path. Okay, so the adder, for instance, used one set of algorithms. The function generators use different one. The shifter used a different one. Okay. We don't use generators as much now as you used to, but they were an important mechanism for us to get a hold of the design problem and try to improve the designer productivity for this new era when chips were getting bigger and bigger by the minute. There are still generators used for memory compilers, is a prime example. There are some used, but not as many as we used to. The early NMOS generators were typically use structured wiring, very simple and structured logic design, and a lot of tiled structures. Okay, so for instance, I think there was some work on placement and routing of standard cells at that point, but that was considered to be a very different approach than generators. Okay, so Could we use generators to help us design larger Josephson junction logic systems? I think so. I think it would require a somewhat different approach, but I think it's possible. You're probably going to need a more sophisticated wiring model in the middle. You're probably going to need some amount of circuit simulation in the middle to help make sure that what you're generating is legal. Okay. So why use generators? Well, you're going to have a lot of regular structures. It will help you build large modules in a reasonable amount of time. And you can also use the generator to explore the design space better. Okay, you can put in different parameters, generate different layouts, then go in and analyze them and say, well, this one, we make this trade-off between area and delay, or perhaps area and reliability. That's much easier to do with a generator than it is to manually generate all these different variations. Okay, so what kinds of generators could you build? Multipliers are regular. That's good. ALUs, similarly regular. Data paths, build upon multipliers, ALUs, register files in order to build another level of regular structure. But what I'm going to concentrate on here today is the programmable logic array, or PLA. Okay, so in general, think about a module generator that takes in some parameters, may have some tools that would actually generate routing, do some checking with simulation, some modeling. So use cell libraries and some parameters from a technology library, combine those together using these algorithms, check them, and you would get out a layout, you would get out a register transfer model, and you would get out some parasitics that are taken as back annotation. Okay, so let's go through the PLA from the Mean and Conway era and understand why it was so successful for a given amount of time. It's based on NOR gates, which in the case of NMOS have a very small pull-up and parallel pull-downs, which was particularly useful, as we'll see in just a moment. So the PLA is organized into an AND plane and an OR plane. There are actually inverters on both sides, but those are relatively small. Okay, so we put inputs into the AND plane. Those values are then sent over to the OR plane, and then possibly inverted on the outside, and that will give us the AND or not functions that we need for a complete set of Boolean logic. One of the nice things about a PLA is that we can also add a register between some of these inputs and outputs and create a state machine. So here is a stick diagram, a simplified layout of a section of one of these PLAs. So the blue lines are metal lines that are running through the middle, in this case, horizontally. So this would be the AND plane, okay? Each row consists of a polysilicon line, that's the gate material, and a diffusion line running vertically, okay? Now, on the left-hand side, you'll see that there is a extra green wire that goes up to this black dot. The black dot is the via that connects that diffusion wire to the blue wire, which is the output of this gate. And then the crossing between the green line and the red line is one of the transistors, specifically one of the pull-down transistors, okay? You'll see in the piece next to it, there's a red line and a green line going across blue lines, but there is not one of these connections, okay? So on the right-hand side, there is no transistor, there is no pull-down. So basically, we can create this grid of wires, and then we can plop down a little bit of extra stuff where we want these transistors. So we can really think about programming the PLA spatially to create certain functions. Okay. So this is a PLA that's used as a finite state machine that's from Mean Conway book. So you can see down at the bottom that 2 of the outputs are connected to 2 of the inputs. That is, and there's actually an extra transistor there to make a register. Okay, so that is the feedback required for the state machine. Okay, the left-hand side is the AND plane. On the left-hand side of that left-hand block, you'll see these funny symbols that look like resistors. Those are the pull-up transistors. So you can see that those are connected to each metal wire. And you can see that there are programming tabs in some positions in order to create pull-down transistors. Okay. The red lines are fed from the top, and they're organized so that you have, I may have screwed up. Yeah. They're organized to give both the true and complement form of the input with a pair of polysilicon lines. Okay, so the blue lines on flow in at the middle to give the output to the AND plane. Those are then connected to the OR plane, which you can see is rotated by 90 degrees. So we use the same structure, but rotated. We can build programming tabs to create the programming of the OR plane. We then use inverters at the output to make sure we have a nice, strong signal. Okay. So based on the logic function we want to build, we know the number of min terms, that is the number of product terms in the Boolean functions. We know the number of inputs, and we know the number of outputs. So we can build this array and then use the particular logic functions in order to put in those programming tabs. Okay. The generator is relatively simple, and I remember I gave a talk at ICCAD many years ago about some layout compaction I was doing, and John Hennessy had a talk about a finite state machine generator that they used an approach somewhat like this. Another nice property of these PLAs is that delay from input to output is pretty similar. Depending, you know, on the average, you can use a single value for delay that's good enough for a lot of purposes. Okay, so it's a nice regular structure, gives us nice regular properties, not just in physical size, but also in properties like delay. Okay, so it seems to me that the Josephson junction era bears some comparison to the early VLSI era, where we're at levels of integration that are comparable to some point in the late 20th century. We have some challenging circuit problems, and I think that using generators and structured design methods is an interesting approach that we can borrow from the past to help us get a handle on the design of logic for this exciting new technology.